Okay, I'm going to start with chapter 8 video, and chapter 8 covers chemical reactions. So in this chapter, our main focus will be talking about um, balancing the chemical reaction. Before we balance it, how can we tell a chemical reaction is actually taking place? So when is a chemical reaction taking place? How can we tell? We'll talk about the 5 evidences that let us know that chemical reactions are taking place. We'll balance the chemical equation, and then we'll look at types of chemical equations. Okay. So I'm going to go straight to the first slide. I usually skip over the goals, and hopefully you can read the goals at your own time. We can tell a chemical reaction is taking place when we see one of the following, at least a minimum of one of the following. We can see all of them occurring at the same time, but our goal is to at least see one of the following, okay? A change in color during a chemical reaction alerts us the chemical reaction is taking place. Sometimes we track the progress of the reaction by tracking the progress of the color formation or the color disappearance. When a color is being made or the chemical that's disappearing is actually colored, okay? The second thing we look at is the formation of the solid. Depending on the size of the solid particles, it may appear, the solution may appear like a milky color with the fine mist of the solid product, or it may look more heavy. And with time, when you form a solid product with time, if you kind of leave the product undisturbed in the solution, the solid product will settle down, and then you can see where it looks like a solid when it precipitates on the bottom. So the solid product here, it's called a precipitate. And then we have the formation of a gas. In the formation of the gas, we actually see gases in the form of bubbles. When it bubbles in the solution, this is usually formation of a gas. And with the formation of a gas, there can't be a logical explanation like heating. If you're heating and getting gas bubbles, that may be due to boiling, right? But we're talking about a formation of a gas when no heating has taken place. So here we see bubbles. Next thing is, once again, you're not around any heat source, but out of nowhere, you have a chemical reaction producing heat, becoming very hot, or the opposite, becoming very cold and taking the heat from the environment. So either absorbing heat from the environment or releasing heat, these are all signs of a chemical reaction. Then here we have emission of light. So when a chemical reaction all of a sudden glows and produces a lot of light that wasn't there before, we can tell something has changed and we have some kind of chemical change, proving to us it's a chemical reaction taking place, okay? Okay, so now we're looking over here and we're looking at the color change. So we have 4 pictures here, A, B, C, D, and these 4 pictures are showing us a reaction as time is going by. So this is the first picture showing us time equals 0, meaning this is right at the beginning of the reaction. The beginning of the reaction, we see a purple color. Okay, so this reaction can proceed anyway. We don't know what's going to happen. But with time, after 2 seconds, we see the purple color slightly lighter than the original solution, right? So we are assuming the purple color is disappearing. The chemical producing that purple color is getting consumed or used up. So we see less purple color, which means less amount of that chemical is present over time, okay? 15 seconds later, we have less chemicals. 41 seconds later, it's almost like it's completely gone. And so with the more time you spend waiting on this chemical reaction to take place, you will eventually notice the chemical producing the purple color will be completely consumed. And then the solution will become colorless/clear, okay? So we're using the chemical reaction to let us know the reaction is taking, we're using the color to let us know the chemical reaction is taking place. Okay, next evidence we're seeing here in picture form is the formation of solid. The solid we're seeing here that's producing a milky color, the swirls, the milky swirls. This is a very fine solid, okay? Now, in general, a solid product is called a precipitate. So solid product is a precipitate. A solid product, oops, I wrote beyond, so let me write in the bottom here, precipitate. A solid product is a precipitate, okay? Now you can have very fine particles in the solid or heavy particles. With the heavy particles, they tend to precipitate down immediately when they're being formed because they're heavy, they're dense, they're weighty, right? The ones that are very fine kind of swirl around in solution and then eventually they settle down. Here we're seeing evidence of gas formation. How can we tell? We're seeing bubbles, and then of course there's an absence of heat. This container, the beaker, is sitting on a table. There's no heat source, right? So the bubbles we're seeing here is coming from the interaction or the reaction between the tablet and the water. And we can see the called effervescence, the release of many, many tiny bubbles, right? Once again, this is an evidence of a chemical reaction. And then we do have heat and light. Sometimes these are released concurrently together. The heat is released when the light is released and vice versa. We see a chemical reaction here where we have burning of natural gas. And the burning of natural gas is producing both heat and light as part of the chemical reaction. So we know a chemical reaction is taking place when we are burning natural gas, okay? And then we have those reactions that are called chemiluminescence, and these tend to release light as part of the chemical reaction. And once the light is made, that is evidence the chemical reaction is taking place, okay? And then we have the heat transfer. The heat transfer can be transferring out of the reaction or transferring into the reaction. And so here, since we have a cold compress, in the cold compress, the heat is coming from the environment into the chemicals. It took me a while when I was listening to them in direction, but when they say it's cold, the reference here is what we as human feels. So if we touch this with our bare hands and it feels cold to us, that means heat is being removed from our hand and is going into the chemicals. So heat is absorbed by chemical. And so this is something I had to learn when I was in school, that essentially cold is the absence of heat. So cold is the absence of heat in the world of chemistry. Now, in the world of chemistry, cold does not travel, only heat travels. So when we say something is left cold or it feels cold, that just means that heat left it. So cold is the absence of heat. So if a chemical feels cold in our hands have lost heat, okay? So our hands feel cold when our hands have lost heat. Even though we're touching the chemical, right? It's this a rule of transfer. So the chemical, our hands feel cold when our hands have lost heat. If our hands have lost heat, something had to have taken the heat. So it's a weird complication thing, but the instant cold compress feels cold on our hand, on our body, or wherever we want to apply it, because the chemicals take in the heat. When they take in the heat, the area that they're in contact with feels cold, okay? Then the opposite is true. The hot compress releases heat. So the area that is in contact with the hot compress feels warm because it has received the heat, okay? So now we're looking at sodium reacting with water. When solid sodium is added to liquid water, a reaction occurs, producing hydrogen gas, sodium hydroxide, solution, and heat. So we have sodium metal here reacting with water. We got sodium here reacting with water. And when they do react together, look, we get a pink purple color. It's like a fuchsia pink, right? More than purple formed. Okay, so we have a color change, a little bit of bubbles here. It's hard to tell, but if you zoom in, there's some bubbles being formed here on the surface. That makes sense because you're producing hydrogen gas. Okay, so here we have our balanced equation showing us that sodium solid reacts with water liquid. Yeah, sodium is a solid, water is a liquid. And then we have bubbles here. Bubbles signify that a gas is produced, which is evidence of this gas here being produced. And then whatever remains in solution form, aqueous solution, is sodium hydroxide. Since it says here that heat is produced or released, that means when you touch this, you see that's the steam over here, probably from the heat. When you touch that, it's going to be very hot, right? So in the lab direction, there'll be a caution saying, be careful. Sodium generates a lot of heat. So you want to approach that cautiously because of the heat that got released. Okay, let's see right here. So we're going to be working on balancing the equation. I will balance first. In balancing the equation, we haven't gotten to that section yet, but I want to go ahead and balance this equation. I want to talk about balancing the equation. We say the equation is balanced when we have, so I'm assuming our equation is completed. We have a reactant on the left side and a product on the right side, right? So we say that equation is balanced when we have the same number of atoms of the elements on both sides of the equation. Okay, equation. So balance means same and essentially equal. We want the same number of atoms of the elements present on both sides, right? When we total them, when we consolidate them, the left-hand side should match the right-hand side. So let's focus on balancing first, and then I'll try to talk about the type of reaction we're looking at. So our goal is to make sure the reactant side has the same elements, element types, as it has on the product side. So the number of atoms have to be the same. I don't mean the chemical formula, just the number of atoms. Okay, what I'm going to do here to balance this, I'm going to itemize what atoms we have in every element or compound, and then balance by multiplying. Then when I'm done with that, I will consolidate the atoms, check the left side, and compare with the right side. So starting with atomizing, right? Sodium only contains, sodium element only contains sodium atoms. And based on this formula, I only have one sodium atom because there's nothing here, so the one is implied. In this next compound or next formula, I have H2O. H2O is a compound. In that compound, I have both hydrogen and oxygen. I have two hydrogens and I have one oxygen, okay? On the right side, I have hydrogen molecule that contains only hydrogen. In my formula, I just have two hydrogens. On my far right side, I have a compound, sodium hydroxide, that contains sodium element, oxygen element, and hydrogen element. Element and atoms are used interchangeably, right, to mean the same thing. Okay, in my formula, I have, remember the nothing here implies one of the formula written before it. So I have one sodium, one oxygen, one hydrogen. Let's go ahead and try to balance. Now that I have itemized, I have listed all the components. Itemizing is like breaking it down, right? I've listed all the components, all the atoms or the elements present in the compound. I can go ahead and try to make sure we have equal number on the left and the right by multiplying. So I'll check first before I multiply. I may not need to multiply anything. I have one sodium on the left, one on the right. I have, let's see, hydrogen, two on the left. I have two here, but I have one here. Since hydrogen is kind of complicated, I'm going to wait to balance it last. You want to balance the more complicated elements last. I prefer doing it that way. You may have your own way. And if your way works for you, I would say stick with that. Work with it until it stops working and then switch it up, okay? So sodium, I have one and one, and then I have oxygen, one and one. Now I have to balance the hydrogens. Here's the thing, if you have an even number of the elements you're examining on the left and an odd number on the right, you want to convert the odd number to an even number by multiplying it. Either doubling is the easiest way to do it, right? Multiply, either double it or multiply by the greatest common factor to make it even from odd. That will make your balancing a lot easier. So I'm going to multiply the bottom hydrogen, well, the hydrogen in the far right by 2 to make that hydrogen an even number, okay? In doing so, I have now changed all these other elements. I have to multiply sodium by 2 and oxygen by 2. So you're probably wondering, why am I doing that? The multiplier I'm using here to make hydrogen even, I'm going to eventually write in front of the sodium hydroxide. But that number that I write here will multiply into all the future, or I should not future, but all the elements written to its right. Yeah, to its right. So for that reason, I have to multiply that multiplier into all the elements in the same compound. That's why I like to write them vertically within the same compound. Whatever I do to this, I have to do to the rest of them. Okay, so now I have 2 hydrogens, I have 2 oxygens, I have 2 sodiums. Okay, now let's do a quick check. I now have 2 and 2 hydrogen making what? Total of 4. Let me multiply the left side by 2 to make 4 hydrogens. So based on what I'm looking at right now, it looks like my hydrogens are balanced, right? We got total of 4 on the right, total of 4 on the left, hydrogen is balanced. But I modified, oops, what did I do? I modified oxygen, right? Now on my right, I have 2 oxygens. I have to multiply this by 2 to make 2 oxygens. But remember, if the elements are in the same compound, whatever multiplier you use to balance or modify one, you have to use the same multiplier on the other, okay? So I really was supposed to multiply that in the first place. Now it looks like the oxygen is balanced, right? Hydrogen is balanced, so is oxygen. And since I use the multiplier 2 here, I have to do the same thing over here, times 2, I get 2. So it looks like everything is balanced, right? Okay, but my original equation is not balanced, it's not modified. How do I modify my original equation to balance it out? I place the multipliers as coefficients. So let me write down here, multipliers become coefficients. And this is how I balance my equation. The 2 I have here goes up here. The 2 I have here goes up here. The 2 I have here goes up here. Okay, so now I have my multipliers as coefficients. That's why it's important to have the same multiplier. I mean, if you put 2, 3, 4, what number do you put before the formula? And whatever number you put here gets multiplied into this, into this, into this. It gets multiplied into the subscript, right? Whatever you have there. So remember, you have 1 here, and 1 here. So 2 times 1, 2. 2 times 1, 2. 2 times 1, 2. Okay. This gets multiplied into this. So 2 times 2, we have 4, right? Then 2 times 1, we have 2. So it they all connect together. Anyway, now my equation is balanced. Let me go ahead and remove all this scratching that I wrote down here. I now want to interpret the physical states of the chemicals. These physical states are important. These physical states are important. Let me finish erasing before I bring up a new thought. Okay, this is 2 right here. Okay, so I hope you've noticed that this one balanced equation actually communicates a lot. There's a lot going on here. It's a balanced equation now. The S, oh, by the way, on the left-hand side of your arrow, you have your reactants, right? Let me see if I can erase this top part here. We have reactants. And in our reactants, we have, let's see, sodium is an element. So I put E for element, C for compound. And then water is a compound. On the product side, on the right side, we have hydrogen an element, and then sodium hydroxide, a compound. So later, oh, we've already learned how to name, right? I forgot, I was gonna say later on. I'm like, no, we've learned this already. We have already learned how to name this, so we should know that, right? Okay, where was I now? The physical states. S stands for solid. So in this reaction, you want to get sodium in the solid form to see the reaction work well. Then L stands for liquid. You want water in the liquid form to see the reaction take place the way you want it to. And then you will experience or visualize hydrogen in the gas form. That's what G stands for, gas. And the AQ here is aqueous. Okay, aqueous, this means ionic compound dissolved in water. Okay, funny thing, when I was learning this in school, the teacher kept labeling certain chemicals aqueous, but never said why. I feel like communication was the key for me taking longer to get chemistry. Stuff had to be pointed out to me, and they just kept saying aqueous. So I'll be like, okay, aqueous. Tomorrow, gas. And I'm like, well, yesterday was aqueous. Why is it gas today? Like, I didn't just know, like, why are you changing the rules? I'm trying to learn as we're going along. But aqueous usually applies most of the time to ionic compounds dissolved in water. Oh, snap. What just happened? I don't know what that was about. Are we still recording here? Let me see. Still audio? Yep. Oh, well, y'all know how that goes. So we've gone over this, so we are good. Okay. When we're balancing the equation, it's saying do and do not. Balance the equation entirely by using coefficients. The coefficients are those numbers, the multipliers that you write before the formula. Remember, those get multiplied into the formulas. Do not do the following. Do not change a correct chemical formula in order to make an element balance. So when you're trying to balance the chemical equation, say for example, okay, let me tell you what not to do. I'm just saying this because when other students, okay, I did the what not to do before I learned what to do. So say H2 plus O2 gives you, you know what I do? H2O2, hey, that's totally wrong. I'm like, what? You can't just squish them together? No, you can't. You can't. That's been there. Been there. I did it already. No, you can't do that. Okay. So they form what they form, right? So H2 plus O2 actually forms H2O, not hydrogen peroxide. And then don't add some real or imaginary chemical species to either side of the equation just to make sure the element balances, right? Then the one thing that they might say later, oh, don't change. I'll just kind of go on my own. Don't change the subscript to balance it out. For example, don't put a 2 down here trying to balance this equation out. Follow the steps that I'm showing you, or if you have your own method, follow that method to balance the equation. Okay. So we're going to be balancing this chemical equation right here. Wait, we already did that, right? So I'm going to do that one again. I did that one. We're going to balance this instead. So like before, I like to separate the reaction side from the product side. So I'm going to itemize what chemicals do I have, or what atoms do I have in this compound. So looking at this, I have compound, a compound, because there's more than one element combined to make that compound. Because I have solid, liquid, aqueous. So let's see. In balancing this, I have, this is 1, right? 1 phosphorus. I have 5 chlorines. I have 2 hydrogens. I have 1 oxygen. I have 3 hydrogens. I have 1 oxygen. No, sorry, 1 phosphorus. Sorry, my mind was wandering. I have to make my mind focus. I have 4 oxygen, okay? Then here I have 1 hydrogen and I have 1 chlorine. Okay, let me make sure, because no, I did have a wandering mind, because it's like mid-thought. So P is 1, Cl is 5, H is 2, O is 1, H is 3, P is 1, O is 4, H is 1, Cl is 1. Okay, now what? Oh, you get to pick what element you want to balance first, or what atom you want to balance first. Let me check P. I got 1 P. I got 1 P. I'm good with the P's. Cl, I got 5. Do I want to do that one first? You know what? Let's make this interesting. Why not try to balance Cl first? Okay. If it doesn't work, I'll try a different one first. So we have 5 chlorines here. I want to make 5 on the right. The only way to balance the chemical equation is by multiplying with a multiplier. So to make the Cl on the right match the Cl on the left, I'll multiply the right one by 5. Let's see if that works. Making 5 here, and then because in the same chemical, I have to multiply the top number, the top element or the top atom by 5 also. Okay, so far Cl's look balanced, right? They look balanced, right? Okay, P is balanced. Now what about oxygen? Oh, you know what? I want to balance the oxygen before I balance the hydrogen. Let's see how that works out. If I multiply the left oxygen by 4 to make it match the right one, would that work out? Let's see. Okay. So P and P match, right? 1 and 1. Cl is 5 and 5. Oxygen, 4 and 4. Hydrogen. Oh, let's say 2 times 4 is 4. Oh my goodness, 2 times 4 is 8. 2 times 4 is 8. And then 3 plus 5 is 8. Yay. No, I was quiet because I was actually thinking ahead. Okay, so when you take the 3 here, you add it to 5, we get 8. Okay, so this is essentially balanced. What are our multipliers? We got 4 here, we got 5 here, and that's about it. So you can leave the others blank because you didn't multiply, or you can put a 1 there. Normally they leave it blank. So these become 4. Oh, my focus today, y'all. Is that whole sleeping late because I was ushering in the New Year's, right? Coupled with, I'm thinking about all the stuff we're going to be doing after I'm done with the video. I'm trying to remain present, yo. I'm trying to remain present. So here it is. Okay. Then let's see. Oh, that's it for balancing? I usually enjoy balancing equations. Do I have more? I have more later on, depending on how long the video takes. I'll try to look at that later on. Okay. Now we want to look at interpreting the chemical equation because this is part of your homework questions. When you're looking at a chemical equation, what information is being given to you? It depends on the context, right? You have particulate level and you have molar level. So they're telling you here that there are 2 main levels you want to be thinking about when you're trying to describe the chemical equation. Particulate level. And so I mentioned this in prior videos that in chemistry, particulate is usually talking about either levels of atoms or molecules, right? When they say particulate, it's not really a lazy way of referring to both, but it's an umbrella term that contains both atoms and molecules, okay? So they say particulate level. So you are going to be describing the balanced equation using these words when appropriate. So in this case, since we don't really have atoms, okay, let me see if I can take a step back. H2 is a molecule because the Brinkelhoff. Remember the Brinkelhoffs, they're molecules of atoms. This is a molecule because it's a Brinkelhoff element. O2 is also a molecule because it's a Brinkelhoff element. H2O is a compound, and it's a compound, so you're going to use the word molecule. It's a molecular compound, okay? So these are the terms you're going to be using. Of the 2 options you have available to you, you have to use molecule, molecule, molecule because of what's going on. So in case you're wondering, when will I use atom? Say you had He reacting with O. Let's make up this, say to form HEO2, something like that. You would, for helium, O2, for helium, you'd have to use atom. If you're wondering, because helium, even though it's a gas, it is an atom. And then for oxygen, you use molecule. And then for this, because it's a compound, there's no metal here, you will use molecule. Okay, so just in case you're wondering, when will I use atom? That's when you use atom, where the formula you're looking at, the individual units are just individual atoms, not molecules. Atoms combined together, right? Okay, back to this. How many molecules do we have here? We got 2, right? This molecule describes this formula here. We got 2 of them, 2 molecules. How many molecules do we have here of this formula? We just got 1, right? Yeah, I'm sorry, this is all scrunched up and this is all stuff going on. But we have one, oops, going back here. We got one. I'll get this right eventually. One. Okay. Woo! Made it. One molecule. And then for the water, we have two. So imagine saying this in words, right? Properly. Two molecules of hydrogen, you could be more specific and say gas, react with one oxygen molecule or one molecule of oxygen. You're describing this to your friend on the phone. Like, you can't believe this. What happened? Well, two molecules of hydrogen gas reacted with one molecule of oxygen gas. What was formed to form two water molecules? I'm sure that doesn't happen with your friends. My friend and I, we both teach, so that's different. This is our career. We both do that. Yeah, so that's how you would describe that very equation in the particulate level. If you were asked to describe the same equation in molar level, then your words or your descriptors will be different. Now you're using moles, okay? Now to kind of mix it up, they use different chemicals. You could use the same chemicals. I'm gonna use the same chemicals. I'm gonna use a different one they use here. I'm gonna use this one here. So this time you would say 2 moles for molar level, and then 1 mole, right? And then 2 moles. So you say 2 moles of hydrogen gas, 1 mole of oxygen gas to form 2 moles of water gas. So let's see what they said here in the molar level. I mean, they use the term molecule here, but you see what I'm saying? So for this one here is 1 mole. And this part here is somewhat confusing. If you're wondering, like, are they just kind of remixing the stuff? Now they're using the formula, the molecule as the descriptor for the formula, which is, I have to admit, it is a little confusing, right? Good news, this is not very common. You don't have to do this a lot, but it's just saying 1 mole, based on this, 1 mole of hydrogen reacts with 1/2 mole of oxygens to form 1 mole of water, okay? While we do use the molecule to describe the formula, it's not as common. So I'm not going to emphasize that so much because I feel like that can be unnecessarily confusing. But the molecule, once again, describes the type of compound we have and the type of bonding. When I'm doing this, I mean the type of compound because we have bonding in compounds, right? Okay, so once again, going back to the particulate level, that explains why these are called molecules and not atoms, right? Why are these called molecules if they're elements? They are elements, right? Why is that called a molecule? Why is this called a molecule? And why is this called a molecule? Why not use atoms? Because they are elements. Don't atoms explain elements, or are atoms building blocks of elements? Yes, they are. But then why are we using molecules? Because sometimes atoms make molecules, and these molecules are still elements. Okay, so hopefully I'm not confusing you, but if you're a deep thinker, you need to resolve this, because that was me, man. I was thinking so deep, I'll get lost in my thoughts. Atoms are individual units, separated. Molecules are units that could have been separated, that have chosen for whatever reason, stability usually, to be combined. So atoms, individual units that stay separated. Molecules, units that stay combined, usually diatomic, that's the most common one. And so they're both elements. So we're seeing here the same type of unit that decides to stay combined diatomically, right? 2 units stay combined. So these are 2 units of atoms staying combined, and so they're called molecules. And then once again, 2 units of oxygen atom here stay combined, and they're called molecules. The ones on the left are molecules of elements. And then on the right, we still have molecule, because molecule just represents any type of atoms, whether similar or different, combined together, right? Molecule just means atoms combined together. So just in case you're wondering, molecule equal atoms combined together. So once again, The descriptor here is 2 molecules of hydrogen. Remember, this is an element. Combining with 1 molecule of oxygen, also an element right here, to form 2 molecules of water, a compound. Okay, same thing here. Oh, this time we have more level representation. 2 moles. So 2 moles is the amount of hydrogen combining with 1 mole of oxygen to form 2 moles of water. So these coefficients here are used to describe moles as in the individual, when you're counting the amounts versus when you're looking at how many formulas you have in the balanced equation. I'm trying not to make it any more complicated than it needs to be. It can be complicated, but we're not going that deep in this class because it's a non-majors class, right? We've seen how to write and balance an equation. We're not going to be completing the equation in this class. I used to teach it before, but I feel like that's for the majors class. So I'll leave that completing the equation for the majors class. Before we look at this here, there are 5 types of chemical reactions we're looking at next. So 5 types of chemical reactions. Okay. The first one is, I'll start with the simplest one. This is synthesis. Second one, decomposition. Third, single replacement. And so in your slides, they somehow throw in redox reaction here. And there is more to redox reaction than single replacement. I just want to let you know they throw that here because I have seen some synthesis reactions being a redox reaction. I have seen some double replacement reactions. But I'm just letting you know that they put this over here. Okay, in double replacement though, for real, we do see neutralization reaction that falls under double replacement. And then we also see a precipitation reaction. Okay. Then finally, number 5, what do we have? Combustion reaction. Okay, so what I'm going to do here is we are ultimately looking at 5 major classes of reaction types, right? And the goal is for you to be able to identify what is what. So I'm going to give you a quick cheat sheet so when we're going over it later on, y'all can see it, okay? In synthesis reaction, the easiest way to identify it is most of the time, okay? I would say about 90% of the time, this rule I'm about to give you will work. There are times when it won't work. Okay, none of our rules in chemistry are perfect to work all the time. So you have an element plus an element combining to give you a compound. So you may have 2 or 3 or many elements. So the way to identify a synthesis reaction is forms one type of product. Okay, that's how you can tell. Synthesis always makes one type of product, okay? Decomposition is the opposite of synthesis, where you start off with has one type reactant. So with this one here, you have one type of reactant breaking down into smaller compounds or many elements. So what we're looking for here, once again, let me highlight the part that you want to notice. The part that you want to notice in this case, synthesis is going to be the compound that is formed, and the decomposition, the compound that's being broken down. That's what you want to notice, okay? And then after that, we have single replacement. With single replacement, you will recognize the single replacement reaction because you have a compound reacting, or the order doesn't really matter, but you have an element and a compound on the reactant side, giving an compound and an element on the product side. So when you're doing like what's it called? Taking roll, On the left side, element compound, most likely synthesis. On the right side, element compound synthesis, right? In chemistry, remember the key is you got to pay attention because what you're looking for is the pattern. Double replacement, what is the pattern we're looking for? Even though it may be neutralization or precipitation, what you're looking for is compound plus compound to give you compound plus compound. So I went from chemistry giving me a lot of anxious feelings, and I was like, I'm not really getting this, to, oh my goodness, I love this, can't get enough of it, right? Because I'm like, this is mysteries, please, right? And this patterns over here, this is my thing, right? With combustion reactions, we tend to have a fuel, but the fuel is a compound. So compound, a fuel. Oops, sorry. And then an element, because oxygen is required in combustion. And then we got compound and compound. So if you're trying to stick with the pattern we have here, because we have patterns, right? EE to give you C, synthesis. C to give you EE, decomposition. EC to give you CE, single replacement. CC to give you CC, double replacement. CE to give you CC, combustion. Okay. Now, is it that simple? No, it's not. But at least we have a template, right? A beginning part to go to build from here on. So let's go ahead and see what they say here. Now they had their own thing, right? Combination reaction is also called a synthesis reaction. Synthesis, putting together, building, right? But you have two or more substances combining to form a single product. So A is written by itself. These are generic terms representing the elements. So you can see A stands for the element, is written by itself. X stands for another element written by itself. So we got A, element, AX. And then you see how they're combined together, the elements combined together, that's a compound. So that follows our E plus E to give you C format, ergo synthesis. See what I'm saying? You're looking for that pattern, man. You gotta find that pattern. EEC, is it EEC or is it CEE? Okay. Now in the actual example here though, they have the particulate form, right? The pictorial form, he uses the picture, particulate form here. Remember, because these are the two circles from the same element combined together, they're still considered an element. We saw this before in the little worksheet I gave you. Why do I sound a little slow? Okay, it's better now. Whoa. Okay, remember, when the atoms are apart, but they match in color and in weight and in size, they're from the same element. Even if they're stuck together, but they match in, they look like identical twin atoms, they are still considered elements. So this is an element, this is an element. So these are together many elements. Same thing here. This is still classified as element. Why? Because the atoms look like twin atoms stuck together. Okay. Now here we have a compound. How can we tell visually we have a compound? The white sphere doesn't match the white, sorry, the red sphere doesn't match the white sphere. They don't look like twin elements. The red doesn't match the white. So that makes the compound. You have different elements or atoms combined together. So once again, we have the EEC pattern. So synthesis. Okay. Oh, I'm going to be balancing this. And this, by the way, is an example of synthesis. How can I tell? Aluminum, element by itself, element. O2, two of the same element, right? But they're twin atoms, right? The diatomic Brinkelhoff, it's still an element though. It's O and O. These are Al and O, different, combined together, compound. Different elements connected together to make a compound. So we got the EEC pattern. My English is getting messed up. This is synthesis. Synthesis, right? Oh, now we're going to balance this. So to balance, I have one Al. I have O, which is 2. Al, I got 2 here. O, I got 3. Right, I have to write these vertically once again because they're in the same compound. So let's see. Do you want to balance the Al first? Sure, why not? Let's make this interesting. Multiply the left Al by 2. We got 2 here. 2, Al's a balance. What about my oxygen? I have an even odd situation. Even odd situation, right? So I have to make the odd even, and the easiest way to do this is going to be by doubling it. But if I double the oxygen, because the oxygen is the same formula as the aluminum. I have to also double the aluminum. Doesn't that mess this up? We'll get back to that. Okay, let's double this. We get 6. We double that. We get 4. Let me deal with oxygen first. I have 6 here. To make this oxygen, 6 multiplied by 3, and I got 6 here. Okay. Now aluminum. Aluminum is 2 times 2 to get 4. I have to go back here. Sometimes you have to go back and change what you thought you already balanced. It happens. Times 4 to make 4. Now let's do a quick check. We have 6 oxygen on the right, 6 on the left. So that's balanced. 4 aluminum on the right, 4 on the left, balance. Multiply 4, multiply 3, multiply 2. So now 4, 3, 2 balances the equation. So from this, we can tell what kind of equation this is. You know what I just thought about? I forgot to mention this earlier, though it does apply. I forgot to describe the heat. Oh, you know what? Sorry, ignore the screen. Let me scroll a little slower. The scrolling the screen doesn't bother me, but if it bothers you, just, yeah, excuse me. If you have heat on the product side, heat product, the same thing as heat produced. Any reaction where heat is produced, given off, is exothermic. So heat is exiting, leaving. And then heat absorbed reactant. Okay. It took me a while to kind of get the gist of that. So if heat is absorbed, it's going to be on the reactant side. If you put heat right here, it's going to be absorbed. So that will be endothermic. Okay. Where heat is required for the chemical reaction. Wow, it got dark really quick today. Okay, let's see. Oh, we're to balance this, right? 4, 3, 2. Oh, we are continuing the type of reactions according to them. Decomposition, that's the one that we have the CEE pattern, right? You can see C, compound made of different atoms connected together, right? Then E, individual atoms, right there. In this balanced equation, how do we recognize this as a compound? Okay, hydrogen is an element and oxygen is an element, and they're combined together, so they make a compound. H2 is just twin atoms connected together, diatomic, right? So they're still elements. O2, twin atoms connected together. So still elements, diatomic molecules, right? They're still elements technically because you have the same type of element connected together. So we have CEE, therefore this is decomposition. Okay, hopefully you can see how easy it is to identify these. And then here we have, I told you guys, on the single replacement, they have oxidation or redox reaction. We're not gonna do anything with this in this chapter. We're gonna just look at it, okay? So over here, A, let's see. Okay, so A is the element by itself. BX is the compound. AX is the compound. And then B is the element by itself. Okay, so we have this right here. So you can see in this chemical reaction, someone got replaced. A single element, ergo single replacement, replace another element. So here, when I was learning this at some point, right, some parts of chemistry were a little dry for me. So I'll add in some humor or some drama. I needed that energy, right? And so for here, I was like, oh, so the yellow element here, they thought things were okay. They're in a relationship with the green element. Things look good. They don't know they're about to be replaced, right? And then the red element is here by itself, like, oh, I'm living a single life. Then before you know it, the red element, because it has an affinity, a stronger affinity, the green element leaves the yellow element and goes after the red element. Now the yellow element was unsuspecting, like I didn't know stuff was wrong. I just thought things were okay when they asked the yellow element, what happened? I don't know. I just found myself newly single. That's B. And then the red is now combined with the green. Okay. So I remember when I understood what was going on in the chemical reaction, it broke my heart. I'm like, but green, why not stay with yellow? What did yellow do to you? It's not personal. These are not people. It's not personal. They just have, the green has a stronger affinity for the red. And I'm like, but green, why can't you just be satisfied? This happens in elements also. I thought it was just people. You have a stronger affinity. But when B ends up by itself, most of the time it's usually a gas like hydrogen gas. It combines with itself to become stable. It has this support group, another element of itself to become stable. So that made me feel a little better. I don't know. I was probably internalizing this a little bit too much, but yeah. In this case here, the one that can cause newly single is not a metal, right? But it's stable. It is stable. It does well in life. Okay, let's see. Copper is an element. Since we have many of these letters here, definitely a compound, right? Many letters here, many elements, compound, a single element, element. So we got ECCE. So this is classic single replacement reaction. Then we have to balance this. So in balancing, I got copper, 1. Oh, I didn't separate the reaction from the product. Silver, 1. Nitrogen, 1. Oxygen, 3. Copper, 1. So I'm just reading the numbers down here, right? This multiplies into here. Nitrogen, 2. 3 times 2. Oxygen, 6. Silver, 1. Okay? So copper matches silver, 1 and 1. Nitrogen, 2. So times 2 to make nitrogen the same on both sides, times 2 because they're in the same compound. I end up with 2 silver, 6 oxygen. Okay, so let me double check. Copper, 1 and 1. Nitrogen, 2 and 2. Oxygen, 6 and 6. Silver, 2 and 2. Now everything is balanced. So multiply here, put the 2 up here. There's no multiplier here. The multiplier here is 2. So 1, 2, 1, 2. That balances that equation. Oh, they go through that, they balance it. Okay, so last but one reaction type. This is going to be a double replacement reaction. A double replacement reaction, you're seeing here, you have a compound and a compound, a compound and a compound. Now with this one here, it's like a line dance. And let me tell you about my line dance experience. I'd watched them on TV. You know how you're looking at stuff on TV about another country that you're hoping to move to later on? That was me. I had seen country movies where they're doing line dances. With your partner. And I'm dancing. And when I actually had a chance to do a line dance in Mesquite, I'm like, this is what's up. This is about to go down. And we're dancing, we dance around each other. We never switch partners. And I'm like, what? This whole time I've been teaching that you switch partners in the line dance. I'll keep using that line because I saw it on TV. I don't know if it's true. But the one time I did do line dancing, we never did switch partners. Okay. So A is partnered with X. B is partnered with Y. Then they switch partners. And they have to switch the right partners. So the first switches with the first, right? So essentially, red goes off the first element on the first one, goes off the second one on the second one. You get what I'm saying? So red goes off with blue, and then yellow goes off with green. And then the order matters too, right? In the formula, in at least in compounds, the first element tends to be the cation. The second element gets to be the anion. Cation, anion. So in the product, the cation is usually written first. So does the order matter? Yes, it does, if you wonder, right? So the red is written first, and the blue is second, then the yellow first, and the blue. I mean, sorry, what color is this again? Green. Sorry, I'm being a lot chemistry and forgetting basic things like color. Okay. So once again, you have the switch, right? Switcheroo of partners, and then we have products. So do I have this? I have to balance somewhere. No, it doesn't show up to balance somewhere. But here we are. So sodium chloride. I know it's just by looking at the reactions, I know where this is going, right? Because this is a compound. So it's got to be compound on the product side. We see switching partners. Sodium switches partners with nitrate. Silver switches partners with chloride. So sodium nitrate, silver chloride. Once you see that pattern, man, the mystery is like, now every time now where you look, you're like, ooh, double displacement, single displacement. Yeah. Once you see the pattern, you can't unsee it. Well, that's me at least. Once I see a pattern in something, it's hard because my brain becomes zoned in on the pattern. All I can see is the pattern. Can't see anything else. Okay, so once you see that, remember I mentioned this underneath, below, or under the umbrella of double replacement reaction, you have neutralization reaction, and then you have precipitation reaction. So neutralization reaction, this is just a type of double I just thought, replacement, that's the term they use. Some books use replacement or displacement. Double replacement, that's what you guys use in your book. Reaction. You can see displacement, replacement. The point is one is going out and the other one is coming in. Neutralization reaction, it follows the format of double displacement reaction. So in the end, you're going to have compound plus compound to give you compound plus compound. That's the bottom line. What these compounds are is where you have either neutralization or precipitation. Okay, take a step back to define terms. We've seen acids before, right? Acids, these are compounds that give up their hydrogen ion when they get in water. Bases, so hydrogen ion are known for having H and then other compounds or other elements. Bases are known for having a metal and then hydroxide. So acids, in the general chemistry class, we call acids Ha, where it's like H, acids tend to have hydrogen, and then A is the other, right? And then bases tend to have metals and hydroxide. So we call it more like Ha and Mo, right? And so bases are known for having hydroxide ions. Once again, in chemistry, it's about pattern recognition. So you want to see an identifier element. So hydrogens are known for having H+. Bases are known for having OH-. Since water has both, water is known as neutral. Okay? It's neither acid nor base. It's the product of neutralization reaction between the acid and the base. Okay. So I know this is double displacement or replacement because they have a compound. Since one of my compounds here is water, I can tell this is a neutralization reaction. We have an aqueous product here and water, okay? We have a summary here. Oh, we haven't done combustion. They didn't show combustion. Okay, hold on, guys. Let me go ahead and add combustion. I didn't realize they didn't show combustion. So I'm on the end yet. I haven't done combustion. So with combustion, and I realized something. I didn't show precipitation either. In precipitation, remember, so yeah, in precipitation, we have two reactants. And one of the product is a solid. So let me see a case. Let's say barium nitrate reacts with sodium sulfate. Yeah, this is going to give me what I want. The product here is sodium nitrate and barium sulfate. Okay. So barium sulfate happens to be a white solid. Okay. But everything else here is a clear, colorless liquid. So what is precipitation? A reaction which produces a solid from clear reactants. Oh, I can't spell. Brain, hang in there. Reactants, okay? A reaction which produces a solid, we have a white solid here, from clear reactants. So the reactants start off, these are clear. When we say clear here, we mean not solid. The color doesn't really matter, okay? The clarity we're talking about here as is there's no precipitate, nothing floating in there, just clear. Color not important, but they happen to be clear and colorless, both of them. Clear and colorless. But when you mix them together, all of a sudden you get a white solid. So this is called a precipitation reaction because it forms a precipitate. So this type of reaction follows the format compound, compound, and compound, compound. So this is the second part of our double replacement reaction. Then finally, I'm going to end this chapter with combustion. Now, I have a little handout here that I'm going to go over it real quick, and then we'll wrap up the chapter. Combustion. How can we tell combustion reaction? This is the format I have, C plus E to give you C plus C. Not always that simple, but most of the time, okay? In combustion, you're gonna have a fuel. This is additional information. Some kind of fuel, because combustion is all about burning. You gotta burn a fuel. The fuel is gonna be burned in oxygen. Oxygen is a necessary requirement for combustion. I learned that my first semester of teaching. I'm a new adjunct. I'm all young and hopeful. I'm teaching, and then I've watched the safety video about what to do in the lab just in case there's a fire, because it's a chemistry lab. We burn stuff. There could be a fire. You never know. That's why you tie your hair back and everything. My hair is tied back. I'm all young, whippersnapper, excited. We're doing an experiment. One experiment called for taking, was it like, I think it was like 0.3 milliliters. Yeah, it was a fraction of it, of some kind of fuel, right? Organic compound, and then lighting it on fire. That kind of fun experiment, right? So everybody's working in the hood, they're lighting on fire. So, you know, the first group lights on fire, second group lights on fire. So then while they're working, somebody says, can you help me out with this? So I turn my back on those who were lighting things on fire, and I'm helping somebody out with their lab, and I hear fire. Okay, these are not the kind of words you want to hear when it's your first semester ever teaching. I turn around and I see flames in the fume hood. Thank God they were in the fume hood where the experiment should be taking place. Oh, thank God. Fire. So I remember watching the safety video I've watched, right? It says, when there's a fire, take the, what is it called, fire extinguisher out, and then, you know, remove the little hose, get to the fire, point the hose at the base, and then press. I remember all the acronyms. So I'm going through my head, I'm going for the fire extinguisher. This older gentleman who has life experience, right? And he's still, the class he was taking was basic chemistry, like this class, right? But he has life experience. He just goes over to where the fire is and pulls down the sash. So I watch him do this, and I'm like, what is he doing? And then the fire just dies down as I'm walking there with my fire extinguisher in my hand. Now, the protocol said I was doing what I was supposed to be doing. That's what I was supposed to be doing. So I wasn't in the wrong. It's just my process is going to take longer. He had life experience, and he knew, man, you just pull this down and then the fire would die. I got there and I'm like, oh, it's dead. Because if you're going to burn anything, you need oxygen. By him pulling down the sash, he killed the oxygen. He didn't really stop the oxygen that was present. He just cut off any more oxygen from getting in there. So the fire burned off all the fuel and burned off the oxygen available, and then the fuel ran out, and then the fire just died. Everybody was good. Now they're like, only my fire extinguisher. I put it back. Thank God I didn't have to use it. Thank God I didn't have to do any report or anything. But so from then on, I'm like, don't start any fire without me being present. I'm gonna watch you. So now on campus, when we're about to have fire, I'm like, I'm gonna stand close by. Nobody, when I'm doing fire parts in the experiment, I'm not listening to anybody else. Everybody else has to be somewhere else, and I'm just focusing on the fire. Anyway, no, we still do fire stuff, you know. I love it when we're doing fire stuff and people get excited, some people get scared. It's all part of the experience. You want to live life, y'all. Experience the fires in chemistry. Anyway, so back to combustion. Combustion reaction, we're almost done, guys. You gotta have a fuel source. And if the fuel runs out, the reaction is over. The burning is out. If the oxygen runs out, reaction is also over, right? So fuel, and then carbon dioxide gets made, and then water gets made. So most of the time, you have something that's carbon and hydrogen in here, sometimes even oxygen. So carbon, hydrogen, oxygen reacted with oxygen to give you carbon dioxide and water. Okay, so here we have a compound that's combination of this plus oxygen. The oxygen may be present here or may not be present. Okay, it's not mandatory, but you have a fuel that has at least carbon and hydrogen. It may have an additional oxygen or it may not. And then you have oxygen as the element. So compound element to give you compound plus compound. Okay, so here, I'm not going to be trying to balance, oh, you know what, guys, I realized something. I do want to balance some combustion reaction because combustion reactions aren't the easiest to balance. So before I get into this last page, I did say I was almost done, but I'll be done soon. Let me do an even number combustion reaction. I'll do an odd number. So let's see. I'll do CH4 plus O2 to give you CO2 plus A2O. So here I have one carbon. Here I have 4 hydrogens. Here I have 2 oxygens on the reactant side. On my product side, I have 1 carbon. I have 2 oxygens. I have 2 hydrogens, and I have 1 oxygen. So carbon, I have 1 carbon, right? The carbons look balanced in the beginning. These look balanced. So let me try to balance the hydrogen. I'll multiply this by 2 and multiply this by 2 because they're in the same formula. Right? And let's see what happens. So I have 1 carbon, 1 carbon. I have 4 hydrogens, 4 hydrogens. I have 2 plus 2 oxygens. I need to double this to get 4. So now I have a total of my oxygens, 4 oxygens. It looks balanced to me, right? Y'all see that? Okay. So I put 2 here. I put 2 here. This looks balanced to me. I see I have 4 hydrogen. Well, I have 1 carbon, 1 carbon. 4 hydrogens, 4 hydrogens. 4 oxygens, 2 plus 2, 4 oxygens. Okay. Let me see the C3H8, how that will work. And if this doesn't get complicated, I'll use one where the carbon number is even. That might get complicated. Okay, so we have 3 carbons and we have 8 hydrogens. We have 2 oxygens and I have 1 carbon and I have 2 oxygens. I have 2 hydrogens and I have 1 oxygen here, right? In the combustion reaction like we have in this case here, balance either the carbon or hydrogen first, do the oxygen last, because we see the oxygen is available in 2 compounds that are different, right? So you want to balance oxygen last. So over here, let me see. It shows that I have 3 carbons on the left. Let me multiply the right side by 3 to balance carbon. I end up with 1 times 3, 3, 2 times 3, 6. So it looks like my carbon is balanced, right? 3 and 3. Now my oxygen, I have 6 and 1. So I'll try to balance the hydrogen first before I get to the oxygen. For hydrogen, I have 8 on the left. Trying to get the right one to be 8, so times 4 times 4. I end up with what? 8, 4. This is another good one, not bad. I'll do an even number next. So 3 and 3 balance, 8 and 8 balance. Total oxygen is what? 10. So times 5 to make 10. 10 and 10 balance. My coefficients, 5, 3, 4. Okay. Let me do one where the carbon is, let's say 4. 4. This is going to be 10. Yeah. So it's CnH2n plus 2. That's the format, the template of that formula. Okay, CO2 again plus H2O. Hopefully you're seeing the pattern as I'm writing this out, right? Okay, let's see. Carbon, we have 4. Hydrogen, we have 10. Oxygen, we have 2. We got a separator. Carbon, we have 1. Oxygen, we have 2. Hydrogen, we have 2. Oxygen, we have 1. Okay, we do the oxygen last once again because the oxygen spans over 2 different compounds. With oxygen, it's complicated. Do the carbon first. So carbon here, I'm trying to get this, trying to get the one on the right to 4 times 4 times 4. So we end up with what? 4, we end up with 8, correct? On the right side, I'm trying to get the hydrogen to be 10. So I multiply by 5. But in the same compound, I have to multiply this oxygen by 5. So we end up with 10. We end up with 5 right here. So hydrogen looks balanced. Carbon looks balanced. But my total oxygen here is an odd number. And then here I have an even number. Uh-oh. So what do? Take a step back. When you have a total oxygen on the right side being an even number and the one on the left being an odd number, do what we've done before. Double. So when this happens, let me write this in words. If total oxygen atoms on the right I'm like, okay, a total oxygen number. I know what I'm trying to say, but I'm struggling how to write it out. The total oxygen on the right was the odd number. Was an odd number. Okay. Multiply carbon and hydrogen by 2. Then balance oxygen over again. Okay, this is how I can think about it. I don't know if this is the most articulate way to say it, but you want to go ahead and go back and double carbon and hydrogen. So I'm going to go back to the beginning and double carbon and hydrogen, making this 8, making this 20. Now my target, my goal for carbon and hydrogen is double what I started off with. The carbon now has to be 8. The hydrogen now has to be 20. So now I'm going back with that in mind. And I'm going to change all of these right here. Because I have a new target for my carbon and my hydrogen. My carbon is now 8. So 1 times 8 times 8 to make 8 to make 16. Hydrogen, my target is 20. So 2 times 10 to make 20 times 10 to make 10. Okay. Now my carbons are equal at 8 each. My hydrogens are equal at 20 each. Now my oxygen total is equal to 26 times 13 is equal to 26. Remember the number I had here before was 13? So in the end, you're going to end up multiplying the right side by 13. And that will just kind of change everything else. Yep. Now I'm done. Oxygen total is 26, 26. So multiplier 2, 13, 8, 10. And now this is balanced. I finally got those numbers I was looking for. Okay, so hopefully you're seeing that. Okay, I'm not going to go through and try to balance this. I want to talk about type of reaction. Let's see. Is that balanced? Oh, they want us to balance these. I want to talk about type of reaction right here. I don't want this video to be too long. So type of reaction. I got to oops, why won't it let me write? Okay, compound, 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 double replacement. Okay, elements, compound, compound element, single replacement. I've been balancing a lot, so feel free to balance some more. Compound, 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 double replacement. Remember, the compound is made up of more than one element that's identifiable. Element, compound, compound element, single replacement. Why did they mix it up? Okay, you know what? Double replacement would be DR. Single replacement would be SR. DR. SR. Element, element. Small compound, big compound. Okay, so here's what I was telling you before. Sometimes not really simply EEC, because we have EECC, right? We don't have a pattern for that. But you see how it all forms one big compound? They all kind of combine together. That's what it's sometimes called combination or synthesis. This is still synthesis because they form one big product. So the rules I told you guys before about, once again, doesn't work 100% of the time. Here's one of those cases where they snuck in this tiny compound that's necessary to form the product, but it's still synthesis because you're forming one product on the product side, one type, not one in number. Okay, so let's see if we can look at these real quick. Compound, 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 double replacement. Element, elements, compound, synthesis. Compound, element, single replacement. Compound, 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 double replacement. Compound, elements, compound, combustion. See? And there's your carbon dioxide and water because you have your fuel here, right? Compound, 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 double replacement. Compound, elements, compound, combustion. Right? Compound, 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 double replacement. Compound, 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 double replacement. Element, compound, elements, single replacement. Yeah. And we're done, guys. This is it. I don't see it getting any more interesting than this. I'm done with the chapter. My goal was to be done before it got to an hour and a half. I think I'm done, okay? This is it for chapter 8. Any questions, please feel free to email me. Thank you.